everyone. This is Math 111, and this is section 3.7, looking at rational equations. So we've done a fair amount of study about polynomials, and if you create a function by taking a polynomial and dividing it by another polynomial, you get what we like to call rational functions. Now, these rational functions have some niceness about it. If h can be 0, if the bottom can be 0, then the function's undefined there, and you will either have a little hole at that x, or you will have an asymptote. So a hole happens when you are looking at some sort of function that's like x squared minus 9 over x plus 3. This bottom is equal to 0 at negative 3, but this x plus 3 will also cancel, and you get this line, x minus 3, that looks like this. But when you get over to x minus 3 over here, there'll be a little hole, or it's undefined at that spot. Right? An asymptote happens when nothing will cancel if you don't have factors that cancel. See, in this case, you have x plus 3, x minus 3, and that x plus 3 cancels out, and you're left with just x minus 3. That produces a hole in your graph where it doesn't seem like negative 3 is going to be a problem. It seems like negative 3 is actually going to be negative 6. But it's not, because in the original equation, x is not in the domain, so x still cannot be negative 3. Right? An asymptote happens when you have something more like this, and as you look here, sorry, look like that, not that. Right? You get to this spot, and it will get close to this line, x equals 0, but it will never, right there, but it will never actually touch x equals 0. Right. So the domain of these functions, if you have these, the domain is generally all real numbers except where h of x equals 0. Then those x's are excluded from your domain. Right? Let's take a look at some examples. Take a look at 2x over x plus 1. All right, now what you have here, right, is a domain that's all real numbers except x can't be negative 1. So you are going to end up with an asymptote at negative 1, a vertical asymptote at negative 1, right? And what this is going to end up looking like, if we were to like plug numbers into a graph and kind of like plot them, when x is 0, y is 0, because you get 0 over 1. When x is 1, you get 2 over 2, which is 1. When x is 2, you get 4 over 3, so you have 4/3. When x is 3, you get 6 over 4, so 6/4, which is 1 2/3. This is 1 1/3. You will notice that as I get larger and larger here, like as I get up to 10, this would be 20 over 11, right? 20 over 11, which goes in 1 and 11 goes in one time with 9 left over, 9/11. So this is still 11.9 ish. repeating. And so if I do 20, I would have 40 over 21. That would go in one time with 19 21s left over. If I go in 30, I have 60 over 31, goes in one time with 31 29 left over. So what you see here, as this is getting very large, this number is getting closer and closer to the number 2, right? That's if I put 1,000 in here, for example, I'd have 2,000 divided by 1,001. That goes in one time with 999 over 1,001 left over, right? Very close to 2. So what this looks like, so when x is 0, so it's going through. It's coming up this way and getting very, very close and approaching 2, right? Now you notice as you go something large here, large, really big, and large here, this +1 really doesn't make a big difference, right? So like, if you have $1 million and someone's like, oh wait, here's one more, you're like, oh, thanks. Not huge, right? So if you can kind of think of this as being the same as large and large, right? When it gets really large, this 1 relative to the largeness is not going to make a big difference. And so you can think of this as 2x over x. And these x's are the same, they're both really big, and so this just becomes 2. So when you have a rational function where the degrees are the same, where p of x and h of x, the numerator and the denominator, have the same degree, then you will have a horizontal asymptote at the line y equals p sub n over h sub n, where p sub n is the leading coefficient of px, and h sub n is the leading coefficient of hx. So let's move on to what happens when they're not the same. Let's take a look at x plus 2 over x squared minus 1. Now, first of all, just acknowledge that this domain works for all real numbers except 1 and -1. That's what makes the bottom 0. Also, if I want to know where the y-intercept is, if I plug 0 in here, the y-intercept is 0, 2 over negative is -2. Right? That's where it's crossing the y-intercept. Also, I have roots. My roots is what makes this 0, and that's always going to be where p of x equals 0. When the top is 0, the whole thing is 0, and this top is 0. P of x equals 0 when x equals -2. So I have -2, 0 is my x-intercept. It looks like I only have one of those. Now you will notice on this, what I have here is, if I put something large in, large, ignore the plus 2, that doesn't matter, over large squared it more than minus 1, and ignore the trailing things. They don't really matter comparatively to the largeness. Large over large squared is just 1 over large. And when you take 1 and you divide it by something very large, that goes to 0. Okay? So you're going to have a horizontal asymptote, which we also write as HA for horizontal asymptote for shorthand, at y equals 0. So on this graph, it's going to approach 0. Like if I put 1,000 in there, right? It's going to approach 0. It's going to approach it from the top because it's going to be coming down from the top there. It's going to approach 0 on both sides. Going through there. The way that this graph looking, you have these two asymptotes, one at -1, one at 1. Right? It's going to approach 0 from the bottom. It's going to get really close to 0 here at this asymptote. It's going to come down. It's going to cross -2. And then it gets really close to 0 as it gets large that way. Likewise, you're not crossing on this side, but you're going to go down. And it's going to turn around and just get really close to 0 as it gets large that way. And in the middle here, something interesting happens as you end up with this little weird little finger that also crosses at -2 and goes like that. Each time getting really close to those vertical asymptotes on both sides. All right? Let's take another look at... So the rule then here is that if you have P of X, if P of X degree is less than H of X's degree, then you're going to have horizontal asymptote at the x-axis at y equals 0. And that is because, again, you're going to be dividing something not so large for something by something large. All right. Now, so we have another one. Let's take a look at this last situation where you have the degree in the top is bigger than the degree on the bottom. So first of all, where is my domain? I would say, well, x cannot be -1/2 because that's going to make the bottom 0. Where is my horizontal, my vertical, or my zeros? I'm having zeros when the top is 0. So if I put in the square root of 3, I would get 0. And if I put in -√3, I'd get 0. So those are my roots, where I'm crossing the x-axis, and then my intercept is when I put 0 in, which is -3 over 2 times 0 plus 1, which is -3 over 1, which is -3. So 0, comma, -3 is my y-intercept. So those are some critical points. I'm going to have a vertical asymptote here because this does not factor in a way that would make that cancel. These are my roots. Notice they're irrational, and then but they do cross the line. They are real, and then that is my intercept right there. Now, if I wanted to then say, well, are there any horizontal asymptotes here? I would take a look at what this is going to look like. I don't believe that slant asymptotes are part of this curriculum, so we won't talk about them too much. Actually, I stand corrected. Slant asymptotes do play a role in this curriculum, so I'm going to go ahead and review them. So when you have your P of x, your numerator, has a greater degree is greater than the degree of your denominator. You don't have any horizontally straight asymptotes, but you will end up having what is called a slant asymptote. And what this ends up looking like, okay, so this is going to go through the axis at two different spots. I'll show you what that looks like. It's going to go through this square root, negative square root thing, and it's going to come up here, and it's going to get really close to, it's going to cross at, let me see what we cross at. It's going to get really close to, what is it, -1/2, right, like that. And then this other one is going to come over here, and it's going to cross at our -3. So it's going to come over here down here, and then it's going to come down, cross at -3, and then go down. Oh, and then get really close again. Sorry, that's messy, to that -1/2. So we have this -1/2 here. That's our vertical asymptote. Basically, what this slant asymptote is this graph is going to look a lot like a straight line except for in kind of like in the middle where the numbers are smaller. Then it kind of goes up towards your vertical asymptote and down towards your vertical asymptote. But if you like kind of erase those parts, it would kind of follow along this straight line, this slanted asymptote line. So you're like, okay, so how do I find what that slant asymptote looks like? Well, interestingly enough, you use this long division that we were working on, and you divide out your denominator, and you rewrite this this goes into this 2 times, right? This would be 2x. That would give me 2 times. I'm so sorry. That goes in 1/2 time. Good grief. I need 1/2 x. That would give me x squared plus 1/2 x. Change the signs and add. -1/2 x minus 3. And I need to multiply that by, what, 1/4 minus 1/4. That would give me -1/2 x minus 1/4. And change the signs and add. That would give me -2 3/4. So this would be minus 2 3/4 over 2x plus 1. Okay. You will notice here that this line right here, this as you get large, as x's get large, this just goes to 0. So this ends up, as you put in a large number, this baby just goes to 0. But this line right here is a slant asymptote. Like that's what the rest, as x gets large, that's basically what the rest of the graph is going to look like. I'm going to go ahead and graph these for you and copy them into here so you can see what this looks like. You'll notice that I'm going to do the slant in a dotted line so you can see what that slant asymptote looks like as a dotted line. Okay, so as you can see, this is an asymptote, slant asymptote line that looks like it goes right through here. And this is the line. And if you like look at it, see how if you take out this middle part of the graph, like from here to here, where the numbers are smaller, as the numbers get bigger, this gets closer and closer to this line. So this basically looks like that line. Then your vertical asymptote is right here at -1/2 going down this way. That's what a slant asymptote looks like. And you are able to graph these when they have that form of the numerator degree being a greater power than the denominator degree from there. Okay, so we're going to do one last example here for you. I'm going to try to show you how to graph this. Now, on any of these where you are really struggling, you can always plug in points, but you could also use a digital grapher like Desmos to get an idea what this graph is going to look like as well. So you could always plug this into Desmos. If I'm looking at that, notice this guy up here is irreducible. It is not going to function. It's not going to ever be 0. So this has no roots. No roots. If there's nothing I could put into here that would give me 0. This does not equal 0. It's irreducible. I'm taking a positive thing, adding something. It's not going to ever be 0. So this is not going to have any, and this does not factor in any way. So this has no roots. When I plug 0 in, I get -1. So I'm going to have an x-intercept at -1. And when I am at 1, I'm undefined. X cannot equal 1 because the denominator cannot be 1. So just kind of taking a quick look at that, I end up with a vertical asymptote at 1 and a point down here. Now I can plug in some other points to see how this is going to look, but no, I'm never going to come close to, I'm never going to touch the x-axis because there are no roots, there are no intercepts for the x-axis. So now I can look and see what my vertical slant is. If I just put 1 here, and I can use synthetic division here because my coefficient is 1 in front. 1, 1, 1. Take a 1 down. That's 1, that's 2, that's 2, that's 3. So I'd have x plus 2 plus 3 over x minus 1. That's how that would factor. My equation, x plus 2, is my vertical slant. So, and that's pretty easy to graph. I go up to 2, and I go over 1, up 1, and I have a vertical slant that looks like this. So as I am down here, it's going to go up here. I can plug some points in, but you'll see that it goes down, and then it curves down this way. And then up here, we're going to go very close to 1. And then we're going to curve and go up that way. And that's what that graph is going to look like. Okay, good luck on your homework, and I hope everything goes well. Thanks.